Here we have a graph of the force in newtons exerted by a rubber band with the force plotted versus the stretch of the rubber band, the length of the rubber band beyond its unstretched length. Now the force versus stretch curve looks like this, typically for a rubber band. The curve actually extends, it's concave down here, it extends, and it becomes concave up somewhere beyond this. But within a stretch that's less than 30% of the original length of the rubber band, the graph tends to look pretty much like this for most of the rubber bands that I've measured in any case. Not being a rubber band scientist, I can't swear that that's going to be the case for all rubber bands, but I suspect that they'll all behave in a fairly similar manner. Could be wrong. Okay, at least the ones that we give you, at least the ones that you work with, have this kind of property. We've tested it fairly precisely. Okay, now what we see is that for a 0.03 meter stretch, x being in meters, 0.03 meters or 3 centimeters, we get a force of 2 newtons. For 0.06 centimeters, it turns out that the force in this rubber band is 3 newtons. And for 0.09 centimeters, the force is 3.6 newtons. So we have these 3 graph points. Of course, a stretch of 0 meters gives us 0 newtons, so we're going to go through the origin. And we have this curve, this dotted red line curve here. Now we want to find the work required to stretch the rubber band. Remember, work is force times distance. As we stretch the rubber band, if I'm stretching this end of the rubber band, I move through 3, 6, 9 centimeters, or 8 centimeters. In this case, we want to stretch this rubber band out to 8 centimeters, and we want to find out how much work that took. Well, if I stretch the rubber band, let's say I've got a hold of the end and I stretch it out 3 centimeters, this graph is telling me that I'm going to go from a force of 0 up to 2 newtons. And then over the next 3 centimeters, that force is going to rise to 3 newtons. And over the next 2 centimeters, that force is going to rise to something here, which looks like maybe about 3.4 or 3.5 newtons. To find the work required to stretch this rubber band, we want to take an average of all these forces and multiply it by the distance, the average of all these forces that are all the forces that are exerted up to the 8.08 meter point. To find that average isn't easy because the forces don't change linearly. We can't just average the initial and final force because the middle forces are higher than an average would indicate. So in order to do that, there are more details, of course, in your class notes and in the video clips associated with those notes. But what we're going to do is we're going to simply assert here that the work is the area underneath the curve. Okay, the force versus displacement curve. And there are good reasons for that that, again, you'll see on the video clips. To estimate that area, we'll first sketch a triangle from here to here and down. And we'll find the area under that triangle. Now that corresponds really to finding the average of the initial and final force and multiplying by the width of the interval. Because the area of the triangle is 1/2 the base times the height. 1/2 times the 3.5 newtons is 1.75 newtons, which would be the midpoint force according to the triangle. If we take 1/2 of the 0.08 meter distance we stretch the thing times the 3.5 newtons, then we're taking something akin to an average force and multiplying it, the average force being half of the 3.5 newtons, and multiplying it by a distance. When we do that, we get an area which turns out to be half of 3.5 is 1.75. 1.75 times 0.08 is very close to 0.14 meters times newtons, or newton meters, which is 0.14 joules. So the area under this triangle, we're going to say, is about 0.14 joules. Now the area is calculated right here. Okay? And that should be easily visible, but we're going to go ahead and zoom in a little bit just to make sure you can see it. Okay, so we have a triangle area of 0.14 joules. Now the area under the curve, which you can still pretty much see, is greater than the area under the triangle, and we're going to estimate that it's 15% more. Now if it's 15% more, then it's 100% plus 15% of this area, or 115% of this area, or 1.15 times the 0.14 joules, which is about 0.16 joules. So just by kind of an eyeball estimate, we say that if the area under the triangle is 0.14 joules, then the area under the entire curve ought to be about 0.16 joules, or maybe even 0.17 as I look at it. But we just make some reasonable approximation here. Now, if that rubber band is used to project a rail, okay, we stretch the rubber band back just like a pea shooter, but we've got something that we release and it slides along the floor, let's say, as in one of the experiments that you'll see. Then we're going to say that the kinetic energy of that rail will pick up the energy that we put into the rubber band. We put the 0.16 joules of rubber energy into the rubber band by stretching it. When we release it, we expect to get that 0.16 joules back. Actually, we don't get it all back because some of the energy is converted to thermal energy and dissipated into the air, and maybe we only get back 80% of that or 70% of it. However, in a first approximation, let's say that we get back all of that energy. Let's say we have a perfectly elastic rubber band that conserves energy and in that case we get the whole 0.16 joules, so that when we release the rubber band and project this rail across the floor, it gains the 0.16 joules of energy from the rubber band. That implies that the 1/2 mv squared of the rubber band, which equals the kinetic energy, is equal to the 0.16 joules. Now if 1/2 mv squared is equal to the kinetic energy, then we can easily solve for V. Multiply both sides by 2, we'll get 2 ke, and the 1/2 will go away. Divide both sides by m, the m goes away here and appears underneath this expression. So V squared would be 2 ke over m. That's a V squared. The V would then be the square root of 2 ke over m. And that would equal then 2 times the 0.16 joules divided by the 0.23 kilogram mass, or 1.1 meters per second. The units on this calculation are depicted right here. We have the square root of kinetic energy, joules, over mass, kilograms. So it's the square root of joules over kilograms, which is kilogram meter squared per second squared. Remember, a joule is a kilogram meter squared per second squared, divided by kilogram. The kilograms divide out. We have the square root of meter squared per second squared, or meters per second. And that's the unit calculation that shows us that this velocity should come out in meters per second. Now what we've seen here, we've actually seen quite a bit. We've seen that the work done to stretch the rubber band is the area under a curve. We've calculated that area and then set it equal to the kinetic energy of a rail. We expect the rail to pick up that kinetic energy when the rubber band is released. Again, that won't really happen in the real world, but with an ideal rubber band it would. And we would get this velocity.